Okay, video number 3. So I think I left off on the last one, on D with probability. No bus. I don't know if I quite finished it. / freshman. So that again is probability. Given that you're a freshman, the probability of not riding the bus. Okay, so that takes us on to E. Okay, E. What is the probability that a randomly selected student is a freshman and rides the bus? So this would be kind of what we discussed up here in this one. The probability of freshman and rides the bus. So remember, and is kind of the horseshoe one. So freshman and rides the bus. There are 31 that ride the bus out of our total of 139. F, what is the probability a randomly selected student is a freshman or rides the bus? Okay, so is a freshman or rides the bus would be 29 plus 31 plus 25. And that's going to be out of 139. Which is going to be 85 of 139. The reason why that works is this. So here's our freshman, okay? That's our freshman. Here is everything about people that ride the bus. Now you'll see when I do that, this was this circle for the first one, and then this is that circle. And it's pretty clear to see here what number got counted twice. That's 31. I don't want to count it twice. I just want to count it once. So that is where that came from, 85 of 139. Are the events freshman and ride the bus independent or dependent? There are a few different ways to do this. So if I'm not your teacher, you probably know another way, but this is just the way I always think about it. So what I'm going to do is freshman and rides the bus. So I'm going to take the probability just of being a freshman. And my probability of being a freshman is 60 out of 139. And then my probability of riding the bus is 56 of 139. Now, when I multiply these together, when I multiply the probability of being a freshman times the probability of riding the bus, I should get the probability of freshman and riding the bus, or my answer for E, okay? So this is kind of a test. And again, there's another way to do this, but if you want to do it another way, and you know another way, that is certainly fine. So when I multiply my numerators, I get this, and when I multiply my denominators, I get that. Okay, and now I want to know if these two are equal. Now I talked with a lot of you guys about how to figure, is this fraction equal to this fraction? You could reduce, you could turn them into decimals. The way that I like to do it, and it's a trick that I showed a few of you guys, and everyone I showed thought it was pretty cool. Here's how I tell if two fractions are equal. Let's take something simple like a third, and then let's take another fraction that's equal to a third. So let's take 4/12. Now I know we can kind of eyeball those and tell they're the same, but again, we're just illustrating a point here. If I take these two and multiply them, I get 12. And if I take these two and I multiply them, I get 12. If I get the same thing, the two fractions are equal. So if I wanted to quickly test these and I didn't want to turn them into decimals, I could multiply these two, and I can multiply these two, and I can guarantee you you'll get something different. If you get something different, this is dependent. Okay, if you get the same thing, it's independent. 2, use the table to find the following probabilities of a randomly selected game from the Mariners schedule. Probability of a home game. My probability of a home game is going to be all the home games, which is 81 out of 162. With probability, I don't make you reduce. You could have written a half. Probability of a day game Well, there are a total of 45 day games out of 162. Home and day. Home and day is, let's see, day and home is right there. Is 28 of 162. Home given day. Okay, so with home given day, given that it's a day game, how many home games are there? So this tells me my denominator is, the denominator is whatever comes after the line in this. So the denominator is all the day games. And how many of them were home? Probability of home or day. So for this, this is kind of like the one I did before. So I add the home games and I add the day games and I subtract the thing that I count twice. Okay, so my home games is 28 plus 53. And my day games is 28 plus 17. I don't want to count 28 twice. So what I get is 98 out of 162. Probability of night and away, meaning away is the denominator. So that's 81. And then the night games, given that it's away, how many night games are there? Given that it is away, how many night games are there? 64. Away and day is 17 of 162. And this is a trick question. Probability of night or day. Or 100%. All of them, right? Okay. Are the events home and day independent or dependent? So that means that basically, for me, this times this should equal this. Probability of home times the probability of day. It needs to equal home and day. All right, so let me multiply straight across. Question is, are these two equal? So I'm going to multiply these two, and I'll tell you what I get this time. And when I multiply this way, I get two very big numbers that are not the same. So this one is, this one is dependent because I didn't get the same thing. Explain differences between or and conditional probability. So with or, something's kind of getting counted twice, and we have to subtract. And is the middle of the circle, okay? So and is both things happening at the same time, as is conditional probability. So conditional probability is just two things happening, okay? So like this right here, all right? This was the probability of a home game, and then an away game, okay? Two different events. Okay, I'll do a new one for the next